Hi, welcome to this channel. Today I'm going to discuss one of the most important topologies in power electronics for application in drive applications like pump storage technologies or traction power systems. Here you can see the schematic of the NPC topology. We have three legs for three phases. I have named them as A, B, and C. And you see in each leg there are four controllable switches, named here as S1, 2, S4. And you see the DC bus voltage is divided into half, VDC by 2, and the middle point is now then grounded, which is a physical connection, by the way. And there are anti-parallel diodes for the switches, of course, for the operation. To the right, you can see the control strategy of the gating of the semiconductor devices. At this point, I assume that you have reviewed the literature for the control of the NPC converter. Here is a pseudocode where you can see how to gate the semiconductor devices. The modulation scheme that we are going to use today is called the sinusoidal pulse width modulation for that NPC inverter. For that, we take a sine wave whose amplitude is varying from -1 to +1, and two carrier waves, triangular waves, which is high frequency, and amplitude of triangular 1 is running from 0 to 1, and that of triangular wave 2 is running from -1 to 0. So we compare these triangular waves depending on if the sine wave part is positive and negative, and the gating sequence of four switches you can see is then depending on the condition implemented here. Now this applies for all three phases. Let's now turn to the PLECS and Simulink environment and start building up the blocks. I've already opened a Simulink model where we will bring then from the PLECS library the circuit of PLECS. Now the power electronic part that I will implement using the PLECS environment, and the control scheme I will realize them in the Simulink environment. Let's double click here to enter the PLECS environment. Control L to open the library browser, and let's bring our necessary components here. So I'll start with the DC source voltage, IGBT, diode, resistor, inductor, since I want to measure later, I need a probe, and to visualize the curves, a scope. Since I will import the gate pulses from the Simulink environment, here we need an input. So this will connect the Simulink environment to the PLECS environment. And for the local schematic, I will use some go to and from block, from blocks. We also need a demultiplexer. So now we have more or less the components for the topology. Let's start building them here one by one. I want to hide the name. So this implements one of the switches. I will also take the from block so we can save some time. Let's call it S1. We need some copies. Make for the connection of the loads and the diodes in between, I will make some space in the middle. So let's see how it was connected. So we have 4 switches here, 1, 2, 3, 4, and in between we have a diode here, also to the top part and bottom part. Now before I forget, I would like to name them. Okay, this is time to rethink the naming. Since there were 3 phases, and that means there are 3 legs, and I want to name them as for phase A is S1A, this is for S2A, this is S3A, and the last one, let's call it S4A. That means these A phase have the 4 switches as 1, 2, 3, and 4. And we will implement for other 2 phases as well. Let's connect them first. We also have a diode just between this and this. And the same is applicable for the lower part. It's connected here. To here. Let's check the connection. So we have from this connection to the middle point of the DC bus bar, and from this middle of 2 in between switches, we have to the middle point of the DC bus bar. We also need a capacitor, or we can say DC source as a general approach. That this is our VDC by 2. But VDC is the total DC link voltage and divided by 2. Sorry, this connection is not there. Let me check. Yes, it is from between the diodes to the ground, or to the midpoint of the DC link voltage, not from here. From the phases, we will connect the loads only. You see, from A, B, and C, we connect directly to the loads. And from the midpoint of the diode connections here, we connect them to the ground. That means this connection is from here to here. We can take a ground, electrical ground, and connect it here to see specifically the division of the voltage. Now this is a physical connection, as I mentioned, also in reality. Now we can copy this leg. This is too extra. So this part, I need some more space to the right. And we need another copy for phase C. So connect the positive terminals. Same, connect the negative terminals of the DC bus bar. You see this connection. And let's not forget, we need to connect from the midpoint of each phase, midpoint of diode. So this point is connected to the ground. This point is connected to the ground. And let's change the naming of the gates as well. So this is for phase B. This is for phase B, second. And the last one, S4B. Similarly for phase C, S1C, S1C, sorry, S2C and S3C, and the last one is S4C. Change the type. As I have taken for all the from gates as global parameter, but I will leave it as global, but it's always better to take the schematic version of it, since I will not use any other go-to block, so the model is not so complicated. Let's leave them as it is, as they are now. So for the gate, for that I need to show the name, and let's call it gates. I would like to separate the gate signals for each phase, so this I would call phase A gates. And for that we need 4 outputs here. So from the 4 outputs we need to connect the go-to signals. So for phase A we have S1A, we have S2A, S3A, and the last one S4A. Now we can copy and paste 2 more times for phase B and C. Let's call it phase B gates, and this one phase C gates. And of course we need to change the namings as well. C, 2C, 3C, and 4C. So we're done with the gate sequences. Now let's implement the load part of it. I consider an RL load, which is normally the case in practice. I'll call it load R. Load L. So this, I take it phase A, that is connected to phase A here. This is for phase B. I think I need to shift it. But this is connected to phase B, and the last one is connected to phase C. Let's consider this is a star connection on the load side. I'll take a voltmeter to measure the voltages here. Let's measure the phase voltage here once and call it B phase. Another voltmeter for the line voltages. I just connected between phase A and B. Let's call it V line. I take some windows here for all types of plots. The first one, I would call it phase voltage, measured voltage. Second, let's take the line voltage. In the third one, let's take this resistor and measure the current. What I would also like to measure is the phase to neutral voltage, which is in between phase and the ground. Let's call it VAO. If I name this node as O and this is A, so we have VAO. So this was for the current, and the last one is for the VAO, measured voltage. So we're done with the setup here in PLECS environment. Now let's go to the implementation of the gate signals. So here we have the inputs for phase A, B, and C gates. Now we need to implement them here. Let's open a MATLAB file to initialize the variables. I would like to first write the DC bus voltage as 600 volts. For generation of the sine wave, I call the amplitude of the sine to be 1. For triangular wave, let's call it also 1. The frequency of the sine, that's 50 Hertz, and frequency of the triangle is then, let's take the 45 times the F sine. That means the carrier signal has a frequency 45 times the fundamental frequency here. Then I can calculate the time period of the carrier signals to be 1 by F triangle. This will need to implement the triangular waves. I would like to implement the pseudocodes, as you can see to the right, using an M function, MATLAB function. I think it's much efficient than using the blocks. So I'll take a MATLAB function. Let's take a sine wave generator. We can also take a repeating sequence to generate the triangular waves. Yes. Let's start from the sine wave. We call the amplitude A sine. frequency is radian per second, so we have 2 times pi times f sine. For the first one, I would say for phase A, there is no phase delay. I just press OK. For generating the triangular waves, we need 3 points here. So I will call it at point 0, then at point 0.5, and the final point. This is the time values. So multiply to triangle. And since for triangle 1, we called its amplitude to be varying from 0 to 1. So I take 0, 1, 0. So it will produce a triangular wave whose amplitude is running from 0 to 1 and back to 0. Okay. Let's call it triangle 1. Can I just copy to make another triangle? In that case, remember we said at 0 we should have a -1, then 0, and again -1. So this implements a triangular wave to the negative side of the y having an amplitude of 1. And for the sine wave, this is sine simply. Now we need to implement the gating inside the amp file. So I would call this one, let's rename the phase A. Let's get inside. Now remember, this function should generate 4 signals. That means for the 4 switches running from S1 to S4, we need to generate these signals. That means the output of this function should contain 4 variables. I'll call it S1, S2, S3, and S4. And the input should, let's call it phase A. The input should contain 3 variables. I'll call it sine, triangle 1, and triangle 2. The commas are automatically added. That means I should also include a comma in between the variables. And we can start implementing our logic. We said if we have, let's have a look before implementing. So there are 2 conditions. One is positive sign and another for the negative sign. Inside the positive sign, if we can compare to triangle 1, and inside negative sign, we compare it to triangle 2, and then just input the pulses accordingly. So I would say if sine is greater than 0, and if sine is greater or equal than triangular 1, what should it be? So S1 should be 1, S2 should be 1, S3 is 0, and S4 is 0. Else, if this is not the case, then I can copy these 4 variables and I'll call it 0, 1, 1, 0. Let's check. So in the second part, 0, 1, 1, 0. So this is end of the first if condition, the main if conditions. And now we can write the second one. That means if the sine is now less than 0, I can basically copy this part and just adjust the points I need to change. So if now sine is greater than triangle 2, we had S1, S2, S0, 1, 1, 0. And if it is not the case, we have 0, 0, 1, and 1. So with that, we come to the end of our main if loop. So if we have one end and end, yes, so it should be the end of the function. So you see our block of the MATLAB function is now updated. So what we can do is just connect our sine waves here, triangular 1 and triangular 2. Before we continue our analysis, let's check the values first. So load R I will just take as 1 ohms, and load L, let's take 1 milli. And if we run, before that we need a multiplexer. Let's take a max. So what I will check in max is the signals, input signals and output signals generated by the function. So let's take a max and dmax as well. Now dmax we don't need at this point, we just need a scope. We can take a scope from here. We need 3 signals for the max. Yes. Let's connect them to sine, triangle 1 and triangle 2. And for the output signals to observe, we need 4 signals. So we need in total we need 5 windows here. Before I connect it, I'd like to use a go to here. Copy the max with 4 inputs. Let's call this phase A gates. So this is the 4 gate signals connected to phase A, and then we can see if it is working correctly, the 4 signals. Let's call it T-sim. And T-sim we can just simulate for 100 microseconds. I'd also like to write this one just to start simulating using the script. Error. Okay, I will deal with this part later. Let's just uncomment and concentrate on the pulse generation. Okay, we need to adjust some parameters. Let's go to the simulation setup, model settings. TSIM I already had. Let's take a maximum time step to be max. And let's take the refine factor. I'll call it refine factor. Okay. The sine wave is looking a little better. The triangular waves are also looking good. The problem is with the generation of this pulse now. Let's now fine-tune the parameters again. Let's take a stiff solver and reduce the time step to 10 microseconds and see the results. Because I need to update them, rerun. Yes, so sometimes the problem, if we leave the automatic solver setup, the selection in Simulink, it might not give us the optimal results. So what we now see is the pulse generation as we were expecting. So you see we have two triangular waves. The green one is the triangular one and the blue one is the triangular two. And in red in the first window we have the sine wave. So in the remaining windows, 1, 2, 3, 4, you can see the pulse signals. You see, according to the pseudocode of the pulse width generation, once we have the sine wave in positive direction, if the switching is S1 is now changing constantly and the state of S2 is now then fixed, S3 is changing, S4 is fixed. So this logic is now implemented correctly. The one thing that is missing now is to implement the same logic for other two phases, phase B and C. You can check it yourself here that the comparison and the generation pulses are correct according to the MATLAB script. Inductor, this low, okay, this is maybe MATLAB, this is load.l, it's not low. And for the other three, it was correct. I can activate it again. So phase A, so we can take this gate signals and connect it to phase A. This is now done. The same thing we can do now for other two phases. I'll just copy 2 more times. And the only thing we need to change is here. So for phase B, we have a phase shift of 2 pi by 3. That means lagging phase shift. 2 times pi by 3. And for phase C, this phase shift is then 4 times pi by 3. This we need to change to phase B gates. And the last one we need to change to phase C gates. So phase A we already connected. Phase B is also connected, and for phase C is also done. So we are done actually with the implementation. And if we run the simulation, we should be able to see the results. So the simulation is run quite fast and we see the results here. First one I told you, this is the phase voltage. Second one is the line voltages. Third window represents the current, the line current of the inverter output side. And the fourth on the last window is representing the VAO, that is the phase voltage with reference to ground. If we analyze quickly, you see that this is representing the peak value of 2/3 of VDC, which is 400 volt, and then VDC by 2, then VDC by 3, and then 0. The steps here, you can count it. For line voltages, it is VDC, VDC by 2, 0, minus VDC by 2, and minus VDC. So these are the steps. Depending on the switching frequency and also the inductance value on the output side, you can have ripples in the current of the output of inverter. Here you can again check the implementation of the gating sequences for phase B and that for phase C. You can go through each step individually and check if they are correct. So for the basic implementation of three-phase NPC converter, these are the steps to go through. The future videos will deal with some more advanced analysis, including switching losses and power, thermal power calculation, thermal temperature, etc. Thank you for watching and see you in the next video. Bye.